What we're going to do is we're going to begin with chapter 21. Let's talk generically about magnets first. What do you know about magnets? Okay, so first thing to note, we have two poles, so there's polarity of the magnets. Good. There's always a north and a south pole.
Opposites attract?
Yeah, opposites still attract, just like with electric charges. Okay, just like electric charges, opposites still attract. But what we notice here is that with magnets, they have to come in pairs, north and south. Whereas with electric charges, you could have a positive charge by itself, or you could have a negative charge by itself. They don't have to be together. Okay? Whereas with magnets, north and south have to be together. What happens if I cut a magnet in half?
Don't matter.
Why not?
Because there's always going to be two poles.
There's always going to be two poles. So here's what it would look like, right? If I cut this magnet in half, that's what I would get. Well, because of magnetic domain theory, I know that really this is now a north, this is a south, that's a north, and this is now a south. I'm putting it at the corner because it's hard to fit, but really it should be anywhere, centered on the end. Okay, but the idea is this. Inside of a magnet, magnetic domain theory tells me that all of the magnet is aligned toward the north end. Remember, this is how we draw. When we were drawing with a compass, we were talking about the North Pole and the South Pole. Well, magnetic domain theory tells me that any given magnet, all of the domains are aligned. So I'm showing them all pointing to the left in a given magnet at the top. But the magnet at the bottom is split in half. Well, all of those blue lines still exist in the bottom magnet. The magnetic domain is still oriented in this direction. So as a result, remember that these arrows that I'm drawing, they really point to the north end. That's what they're doing. Okay, that's where we come up with the idea of the North Pole. Remember, the north end of a compass would point toward the North Pole, so we called it the North Pole, even though it's really the magnetic South Pole. The whole idea. Same thing applies here. The compass in this case would point toward the North Pole. Well, so if I cut a magnet in half, I still have everything pointing left. So the piece of the magnet that's over here on the right, all these arrows are still pointing left. So this is now the North Pole of this magnet. These arrows are still pointing left. This is the North Pole of this magnet. Well, if this is the North Pole, this has to be the South Pole. If this is the North Pole, this has to be the South Pole. Again, because poles come in pairs. Okay? Poles come in pairs. So, yeah.
So what are those areas representing? Magnetic field? Or?
The blue lines?
Yeah.
The blue lines are those many domains they were called. We call them magnetic domains. When the domains are all aligned, the object is magnetic. Okay? When the domains are all aligned. And there are little like sections. Imagine little sections of this piece of ferromagnetic material. And all of those sections are all pointing left. So we would say that they're all aligned. Okay, they're all aligned. But when we cut in half, they're still aligned. Nothing happens. It doesn't change the alignment. But because they're all pointing left still, we still have a north end here. But now this is like a new north end, because all these are pointing left. So every one of these little arrows is like its own little magnet, okay, which the tip of the arrow is north, and the tail of the arrow is considered to be like south. Okay, so if you wanted to really zoom in and see what I'm saying, okay, each of these is like a north-south every time. These are all like mini north-souths. Okay, that's what magnetic domain theory is really telling us. So when I cut it in half, I still end up with the same exact alignment.
So when you say as in cutting the magnet in half doesn't disrupt the magnetic domain, what does?
What would disrupt the magnetic domain? Another magnet, the presence of another magnet, would cause the poles to realign. Let's see. If you put this magnet inside of a solenoid where there was a current carrying wire, it would magnify its strength. It would make it stronger. Yeah, but it would still be aligned that way unless the field that it was inside of realigned it. So for example, if I take a solenoid, let's combine this. That's a really good example, Summer. A good question to ask. If I take a solenoid and I wrap it around the magnet like this, okay? And the arrows in the wire are showing the current's direction. So I take a solenoid and I put the magnet centered in the solenoid in these loops. The current is traveling up, so my thumb, remember, travels the direction of the current. My fingers wrap around the wire and show the magnetic field is really this way in the beginning of this. Well, if it's this way in the beginning, and then it's going to loop down, it's still going to be in the same loop. So what's going to happen is, we're going to get a magnetic field, and I'll draw this in green so we can see it's a little more obvious. We're going to end up getting a magnetic field that comes out of here, like so. The green is the magnetic field lines. So in this case, what would happen is, and again, the way I know this is because my thumb is traveling up the wire. Take my fingers. Which way are my fingers pointing? To the left. So that means that the magnetic field is going to temporarily wrap around like this and come back into the wire like that. Okay, so again, my thumb is pointing up. If I follow my fingers, they would go like this. They would loop around like so. So I know that the actual magnet, with the field lines of the magnet will come out the end, this end, and loop back around three-dimensionally. I'm trying to draw it this way. Okay, but it would really come out of the page, back around, and loop back into this end. That's what this direction of my fingers is showing here. Okay, that's what I'm actually trying to get at. If the wire were coming down from the top, okay, if the wire were traveling downward and the current was down, my fingers in that case, it would have to be on the back of the solenoid and come around this way. It would still be going this way. So it depends on the orientation of the setup. If it was over here traveling up and it was this way, in this case, it would be coming out of the wire the other way. So it depends on the arrangement of the actual solenoid. What I want you to get is the fact that the wire is producing its own magnetic field, which is making the object in the middle more magnetic itself. And you're creating like a synthetic magnet or a man-made magnet as a result. Now, some of the things we talked about with this, the stronger the current is I, right? I. The stronger the current traveling through the wire, as the current goes up, the magnetic field strength goes up. Remember, capital B was magnetic field strength. That was later on in the chapter. I'll write the formula at the top up here in case you're wondering. It was B equals magnetic force over QV. We talked about with a point charge in space. Well, B is still magnetic field strength. As you increase the current, you get a stronger magnetic field. More current going through this wire, the stronger the field is that's produced by this electromagnet. The more coils there are, the stronger the magnet itself is. Umar, where's your project? Is it in here again?
No, I think Kevin has it.
Is he having with him, yeah?
Yeah.
I was hoping I could see some of the solo parts here. Okay. Well, the idea here is that as you increase the number of coils, so if you were to loop these coils around that magnet or that ferromagnetic material in the middle, if you loop it around more, you get a stronger electromagnet as a result. So the more loops you have, the stronger it is, because the current is technically kind of overlapping itself, magnifying the magnetic field over and over and over again as you loop. Let's see. Let me see what else I want to talk about. What else in section or chapter 21?
Joey Bristol left the group. Accumulated.
So for the thumb test,
Ladies.
all you have to know is that how it goes in and how it goes out for the thumb test.
Correct. For electromagnet specifically, yes. But I mean, the idea of the right-hand rule for the thumb for this is when you have any wire, let's say the current is traveling in this direction. Okay, you take your thumb, put it in the direction of the wire, and your fingers would show you the direction of the magnetic field. So the magnetic field would be looping this way. Let me draw you a little. Okay, it would be like this. Okay? So take your thumb. take your thumb in the direction of the wire and take your fingers and curl them around the wire. Imagine that the stylus is the wire, your thumb is going along with the stylus, curl your fingers around the wire. So this magnetic field will be rotating this way around the wire. That's what you're seeing, this orientation of this. See this right here? That's my fingers coming out of the page on this side and going back into the page on this side on the bottom.
You're saying it's going out of the page. You say like.
Well, it's technically out of the page on this side and
Into the page.
into the page on that side. Okay, because the field is literally doing this.
Yeah. It's
And
wrapping.
it's looping around the wire like that. Now, again, the idea though, as Marco was mentioning, was that if you take wire and loop it into a solenoid, you produce the effect of a magnet. It's the exact same thing as a magnet would be. So we mentioned this in your notes. I'm trying to think back exactly which section it was in. I think it was in 21.2 that we mentioned this, and I gave you a diagram. That'd be a good diagram to study to understand the direction of the orientation of the north and south poles. Let's see. We talked about soft and hard magnetic materials.
And it's still chapter 2.
Still chapter 21. Soft and hard magnetic materials. What was the idea behind a soft and a hard magnetic material?
If it takes more energy to become a magnet, then it'll stay a magnet for a longer time.
Yeah, the idea is that a hard magnetic material takes more or stronger magnetic field to make it into a magnet. But it will remain a magnet even after that field is removed from its presence. Again, this is analogous to specific heat capacity from chemistry. It might take a lot to heat up cast iron, but cast iron retains its heat for a long time. Just like it takes a lot of magnetism strength to make something magnetic that's hard magnetic, but once you remove that magnetic field, it remains a magnet. Something that's a soft magnetic material, it does not take much to make it a magnet. But what happens?
It will not stay.
Yeah, it will not stay a magnet when removed from that field.
Can you say it doesn't take a lot of energy, or is it specifically magnetic strength?
It doesn't take a strong magnet, you would say. Or it does take a strong magnet, depending on it. You could use the word energy, but it's not properly used there. Let me think about what else I'm going to cover.
So for example, they just move the.
As soon as you move so you have this really strong magnet, right? You bring it near a soft magnetic material. It'll become a magnet very quick. It becomes magnetized. But the minute you remove that really strong magnet out of its presence, it'll probably just go back to its unmagnetized state.
So then that.
It doesn't retain it.
Yeah, but the hard magnetic material just retains it forever.
Yeah, but it takes a stronger magnet to make it magnetized. A hard magnetic material takes a lot to make it a magnet, so you need a stronger magnet than the soft one. But even when you remove that hard magnetic material, or that really strong magnet, the hard magnetic material will remain magnetic afterward.
So what does that mean for the hard one when it's not near another magnet or something?
It will just stay a magnet.
It's not, yeah, they're not, it doesn't matter. It'll remain a magnet. It'll stay a magnet afterward. It doesn't have to be in the presence of another one once it's been induced. Remember, this is magnetic induction, similar to electric induction, where you brought the object near the other object. You grounded it, made it a positive sphere. Same idea is that you're bringing a magnet in the presence of the other magnet. Let's see. We talked about what's it called? No, something to do with magnetic. I had it on the tip of my tongue. Okay, I'm thinking of the wrong word. We talked about the idea in chapter 21 of magnetic field strength with charged particles that are moving in that field. So let's take a look at that mathematically for a sec. It'll come back to me what I was thinking of. The number that we're looking at here is magnetic field strength equals magnetic force over charge of the particle times the velocity of the particle.
That's MAG.
Okay, MAG, magnetic field strength. And I think on your formula sheet, I think I might even just write FM. Okay, M for magnetic. And Q is the charge on the particle, V is the velocity of the particle traveling, B is the actual field strength. What was B measured in? Anybody remember that term?
T.
Yeah, what did that stand for?
Tesla.
Yeah, Tesla, very good, Tesla.
The car?
Okay, capital T, like the car, yeah, same guy, Nikola Tesla.
No, yeah, but
Okay, so the units here are Tesla,
what Julia?
these units are newtons, these units are coulombs, these units are meters per second. Okay, so you know what the units are in your terms here. Velocity, charge, force, magnetic field strength. So many people would benefit by knowing their units better in this class, in both classes, in the juniors in general. Okay? You really would help you a lot. A lot of you struggle on the math parts and make mistakes on things where the units signify the meaning of the problem itself. You could utilize the units. If you see coulombs, you should know charge. If you see meters per second, you should think velocity. If you see newtons, you should think force. So the units will help you a lot in these kinds of problems. We did this and we talked about the parameters that affect the magnetic field strength being those three there. So we can clearly see that if in this case, if we solve for magnetic force, okay, if any of these three parameters, field strength, charge, or velocity increase, the force felt by that particle increases also. These are all directly related. We call these jointly related, meaning all three of them join together in some direct relationship to the magnetic force. So if you have a stronger field, the force felt by the particle will be stronger. If you have a stronger charge on the particle, the force felt by it will be stronger. If the particle is moving faster, the force felt will be stronger. Okay, so these three are all directly related to the force that is felt by that particle. Okay, the force that is felt by that particle. Now, what did we do with this mathematically? Who recalls? We did several things here, mathematically. Look at your notes, section 21.3 if you have to. We did two things with this mathematically.
The direct radius of the curvature. Oh no, that's.
We did do that. We'll go to that in a second, Sarah. What did we start off with, though, in this section? What did we begin to learn about?
Oh, I thought you meant like in regards to doing the math. I was just gonna say solve, we're gonna solve it.
Okay. For what specifically, though?
The magnetic induction. There's
The magnitude and the direction.
We found magnitude and direction of something. What enabled us to find direction? What was the idea in this section? It was like a Z direction. Yeah, we did another right-hand rule. Remember this whole right-hand rule here? Okay, this one was like, yeah, we had to take our hand and kind of orient it weird. What was the rule? What was the rule? Start with the thumb. Thumb was in the direction of what?
Your velocity.
Okay, thumb was the direction of velocity, or particle moving. Fingers were in the direction of
B.
the magnetic field, B. And your palm pointed in the direction
The magnetic.
of the magnetic force on a what?
Charge.
On a positive charge.
So
On a positive charge. So let's look at this. Okay, because geometrically I feel like people are going to get confused first.
So this is when you have to say it's out of the page.
Yes, this was out of the page, into the page, that concept. So you've got, let's say you've got a magnetic field acting into the page.
Oh, this is when P is
Yes. All right, so
Is this the only math that like we're going to solve?
it's this and then the stuff on spontaneous emission with E equals H omega. That's in the next chapter we'll get to. So the magnetic field in this case is into the page. Kian, why do I know this is into the page? Remember this one, Kian?
Oh yeah.
Why do I know it's into the page now? Now that we've learned this, what was the way to remember it?
Like if, it's like it's, I forget.
What did I give you the analogy to? An arrow, remember an arrow? So explain here.
2,000 miles.
You're still on the hot seat, Keenan. Think about the arrow analogy. How does that explain that this means into the page?
It's like,
Oh.
Julie,
It's not.
I still gotta review this.
Alright, well if I shoot an arrow at you, what are you going to see? You'll probably see like a dot, the tip of the arrow. But if you shoot an arrow away from you, you'll probably see the feathers on the tail. So think of these as like the feathers of the tail. If you had two feathers crossing and you shoot an arrow, you're going to see them going away from you, it's like an X. If something coming towards you, like a dart coming at you, you'd see the dot, the tip of the dart. So when you see dots everywhere, it means out of the page. X's means into the page.
Okay.
So that's where we have to start. Let's say that the particle is moving left.
Wait, so what is that called in regards to
The right-hand rule, let's go over it. That's what we're going to do.
I mean, like, what part of the equation do we see there? Is that the velocity?
So X is the magnetic field strength. It's representing the magnetic field is going into the page. Okay? The velocity is left. So this is what I've got. Look at my hand if it makes sense. Fingers always go in the direction of the magnetic field. That's into the page. Thumb goes in the direction of the velocity of the particle. If this is a positive particle, the force felt will be down as a result. Look which way my palm is facing. My palm is facing down. So the force felt by this particle, if it were positive, would be down. If this particle were not positive, the force felt would be, yeah, up, not negative, up.
Wait, so X's are
Okay.
on the page and, oh,
X's are into the page, dots are out of the page.
Is that for B?
For anything. I mean, I could say like the velocity is into the page, right? I could do another diagram in the next one.
Oh, you would tell us.
I could say in the next diagram, again, if the field is into the page and the velocity in this case is to the left, then as a result, what we end up happening here is the force acting down. Okay, again, the palm would face down on a positively charged particle. Again, assuming this is a positively charged particle.
So the B would go up, the B is going up.
Okay, again, B is into the page, velocity is left, it's a positively charged particle. So because of that, I take my fingers, I put them in the direction of the magnetic field, I take my thumb, put it in the direction of velocity, down points my palm, therefore the force felt would be down on this particle.
so how would you ask us that on the test?
Determine the force felt and its direction.
But you would do it with either X or a circle? Is it X and
Yeah, anything could happen, guys. Anything at all. Okay, so another arrangement, stop. Another arrangement could look like this. Velocity is out of the page just because we went over this a lot and you guys are asking questions you should really know the answer to already. So velocity, let's say, is out of the page this time. So you start by taking your thumb and pointing it towards yourself. This is different. Again, a moment ago, we looked at the field into the page, velocity left. Now I'm telling you, you have to draw these diagrams. It's all going to be in the problem. The problem on this one, for the blue arrangement, would say, the velocity of a particle is acting out of the page. So you would start by drawing that. Then the problem might say the following. The magnetic field acts up. So you would do this. And I'm using color coding right now so you can see this physically. So you start with your thumb towards you, fingers straight upward. So you're literally doing this with your hand right now. Okay? Which way is your palm facing right now? To the left. So if there was a positive particle, the force would be to the left. If there's a negative particle somewhere in this vicinity, the force would be to the right.
So it all depends on what direction you say the magnetic force is.
Exactly. It depends on the problem itself. Depends on the direction of the magnetic force. the direction of the velocity. It all depends. You have to figure that part out. That's why you did homework on this. That's why your proms had you do this. So depending on the arrangement, if the problem says the velocity is acting down and the field is out of the page, or the velocity is acting right and the field is into the page, or the velocity is into the page and the field is down. Like there's so many possibilities, so I'm not going to sit here and do them all. But the idea of the right-hand rule is that you orient your hand accordingly to determine which way the force is felt. The force itself is felt.
I was only asking questions because I thought you were going to just like give us X's or dots.
Yeah, no, I'm going to give you a word
Okay,
problem,
okay.
and you're going to then draw a diagram based on that.
Makes sense.
So this left word problem would have said, the field is acting into the page with a velocity on a positive particle that's acting left. Which way would the magnetic force be felt, and what is its strength? I'd have to give you numbers, obviously, for you to figure it out. So let's look at the right example. Let's say the velocity of the particle is 20 meters per second. The field strength is 3 Tesla, and the particle has a charge of negative. If I tell you it's an electron, you should know it's negative 1.6 times 10 to the negative 19, because that's on your formula sheet. It's given. If I tell you it's a proton, you should know it's positive 1.6 times 10 to the negative 19. If I tell you it's 2 electrons, it would be negative 2 times 1.6 times 10 to the negative 19. Is that clear by now? Because on the last test, I did this once, and a lot of people got really confused. It was an example a few tests back, actually, about a person combing their hair, and their hair loses 7 electrons, and the comb gains those 7 electrons. Well, 7 electrons would make, instead of a 2 here, you put a 7. This 2 in the front just means like this is really just 2 electrons. Okay, so 2 electrons are, or something with the equivalent charge of 2 electrons is here. So again, take your thumb, point it towards yourself, because the velocity is out of the page. Take your fingers, point them up, because the field is acting up. Since this is a negative charge, the force felt will not be this way, which normally would. Which way will it be?
This way?
Yeah. So the force you're going to feel on this one will be to the right. Okay, to the right. Again, because it's a negative particle. If it were a positive particle, the force felt would be to the left.
So you're not going to say the force is acting over, but the magnetic field is felt upward?
The magnetic field is directed blank. The velocity of the particle is blank to this direction,
But I'm
blank.
just being specific with the palm facing this. So I call that the force, but the magnetic field.
Yeah, so in this case, you would
The
say
magnetic field is working.
the magnetic field is acting to the right.
So what is up?
Your Tesla, your B.
But how would you write that? You didn't just say the B.
No. So are you asking about field or force? Because
I'm
you're
asking
saying
what
both
the
words.
I'm asking what the terminology is for when it's going up. What is that? What's going up?
What are you talking about though right now?
The arrows that are pointing up.
So that would be the field itself.
Okay.
The force, which is what we're trying to figure out, is what's acting either out of the palm or the other direction if it's negative. Okay? So the problem, word problem-wise, would say, a field strength of 3 Tesla acts directly up. The velocity of the particle is 20 meters per second out of the page. If the particle has a charge equivalent to 2 electrons, determine the force felt and the direction of that force. So let's figure that out now. So to find the force felt, we would use this formula here. This formula could be solved for force as BQV. And you have all those values. They're right there on the table or on the diagram. Okay, all I'd have to do is multiply those 3 numbers and tack on the statement at the end, or make the statement at the end, that it's acting to the right. Okay, to the right. Now, Q has a negative number, right? Q has a negative number in front of it. So, what is that negative number really indicating? It's indicating that instead of going left, which my palm faces in this setup, right? My palm faces left clearly. The negative is simply indicating that I should go to the not left, but to the right. So my answer for this, I can write it with all positives. Okay, so if you'd like to, you're welcome to do this. And this is, again, depends on the setup you'd like. You can do this, and then just put at the end to the right. But if you didn't do that, you'd get a negative answer. You'd then have to write, well, it's really the same answer that's positive to the right. Okay, so again, if you're going to do that, put absolute value and put to the right. But if you forget to do that, that's okay. Doesn't matter. You can write it like this. You can do it as 3 times negative 2 times 1.6 times 10 to the negative 19 times the velocity of 20. Okay, you can do this and come up with your force, but normally this would be to the left because you have a negative here. You'd have to get rid of the negative sign and write to the right instead.
So you can't just leave it with the negative sign, it's not like understood.
Correct. Okay, so here, in this case, you could just make them all positive and tack on to the right because you did the right-hand rule. Or you could leave the negative alone, do the right-hand rule, recognizing that a positive particle will move left, so because you have a negative sign here, it's going to move to the right. Either way works, really. It just depends on which way you choose to approach it. We did another mathematical kind of problem with this, where an object continues to move in circular motion, where there's some sort of radius involved and there's a curvature to the path of the actual object moving. So we looked at one that looked like this. It was like the last example in section 21.3, where there's a field acting, let's say there's a field acting into the page. And a particle moving to the right. So we've got a particle to the right and a field into the page. Which way would the force be in this case? It'd be up, okay? Again, assuming it's a positive particle. How do I know to do this? My fingers.
Because you're magnetic. It's
Fingers
magnetic.
face the field, which are x's, so that's like this. Thumb faces the direction of velocity. Okay, so that's the setup I've got. My palm points up. So the force on this particle would be upward. Now, watch what happens. Okay, the particle will start to move upward. As it's moving to the right, follow. It moves to the right, but because the force is up, it'll start to do this. As it starts to curl up, it'll turn. And then it'll want to curl more. And now which way is my palm facing?
To the left.
So now it's going to want to move left, even though it's moving up. So it'll start to curl like this. And it'll start to form uniform circular motion. Okay, so this is the example where the particle feels a force acting upward. That's the magnetic force. And it'll cause it to start to curl, and it'll eventually start to spiral, and you'll get uniform circular motion here. Remembering that
Is that what anyone is?
with specific ones where the fields are consistent, yes. The field has to be consistent. It can't be changing. So with all of these, we remember that something provides the centripetal force, always. In this case, it's the magnetic force. So BQV equals mv squared over r. And this is something you have to remember from earlier in the year. On your formula sheet, you're given that AC equals v squared over r. So if AC is v squared over r, you take this right here, v squared over r, which is A, multiplied by mass, that'll give you the force, the centripetal force acting. Again, remember this is A, really. That's really AC. You would need to know more information. You would need to know the mass of the particle. Okay, you would probably end up solving for the radius of desire here. What should the radius be?
Mr. Howell?
Yeah.
What is the spiral going? Stolen motion? The spiral going around?
It's just circular motion. Just showing circular motion.
Did you say this is on our formula sheet?
Say again?
Did you say this is on our formula sheet? The BQ equals mv squared?
No, it's not. Again, guys, remember, magnetic force equals BQV is on your formula sheet. It's not written that way, but it is. AC equals V squared over R is on your formula sheet. But you need to know that, remember, centripetal force is provided by something. In this case, is the magnetic force. So you have to set these equations equal and solve. It's not, absolutely not on your formula sheet. Okay, that's it for 21.3. That was the last thing for magnetic stuff. I'm trying to think of what else there was for magnets. Anything else? Well, this is definitely one of the examples mathematically you could expect, but that's it for magnetism.
Can we go over what it goes wrong?
Yeah, what happened to
Say again?
If something doubles, then what happens to the other thing, or like if it quadruples? Can we just like go over one of those?
Sure.
We're gonna test my screw.
Sure. Okay, so this is not 23.2 then. We're pausing. We'll go back to 20. There's a question. So say you had this formula here, and you were told that the velocity of the particle doubles, right? The velocity doubles. As a result, what happens to the magnetic field strength? Everything else is held constant, and the velocity doubles. You want the same force applied to that particle.
Because it's being divided by
Okay? You're not using the right words though.
Wait, if you want B to remain the same.
No. Again, guys, this is where you have to listen to my vocabulary. Magnetic field strength is what I asked about. So I'm asking about B, and I'm saying that everything else is remaining the same. Okay?
And that's
So if everything else remains the same and the velocity doubles, what happens to the magnetic field strength?
It's still similar because that whole number is just going to shrink.
Yeah, what you're doing really is you're doubling the velocity, right? It's like putting a 2 down there. So you're reducing this overall thing by a factor of 2. You're cutting it in half. So what would happen to the magnetic field strength? B, it would half in that
Okay.
case. The terminology is important. That's why I spent a minute going over it a moment ago when Julia asked that. Magnetic field strength, magnetic force, charge, velocity.
Okay, thanks.
Okay, again, field strength, force, charge, velocity. All right, so 23.2, let's take a look at 23.2. 23.2, we started with what?
Oh, the model?
What was 23.2?
atomic models.
Yeah, the basics of atoms. And we looked at things like neutrons and protons and atomic number. What's some of the important stuff that you should know from that section? From 23.2.
All the people from the models? Are you taking general? No.
Isotopes?
Say again?
Never mind.
Isotopes?
We talked about isotopes. Good. What does the word isotope mean? What's an isotope?
It's a variation of certain element depending upon how many neutrons it has.
Yeah, the variation of the element depending upon the neutrons. So, an object may have more neutrons and therefore it has a higher mass, which makes it the same element but an isotope of that element. For example, carbon-12 has 6 protons and 6 neutrons. Thus 12 is the mass. But carbon-14 would have 6 protons and 8 neutrons. 8 neutrons. That's what an isotope is. What else? What else from section 23.2?
Atomic spectrum?
23.2?
Yeah.
What do we know about the atomic spectra? For those that did well on this part of the quiz. Was this on your quiz or was this in the other classes?
No, we had a mission.
You had emission spectrum, yeah. What was the atomic spectrum? What was the whole concept behind it? How did it help?
You can see like light that's given off by different elements, so you know which element is in there.
Yeah, you take an element in the gaseous form, you apply voltage to it in a chamber, it gives off some fluorescent light. That fluorescent light is then passed through a prism, which breaks it into what's called its spectrum. And that's exactly what Julia's mentioning. Each element has a unique spectrum. That's the whole concept there, okay? Again, if you have an unknown material and you can make it into a gas and you can apply voltage to that gas, the light that comes out is fluorescent, that gets passed through a prism, broken into wavelengths. The wavelengths that appear there are the spectral lines, and those spectral lines are unique to each element. And this was also what we talked about how, for example, the sun, helium was kind of discovered. Okay, because it came from the light from the sun, from the energy coming from the sun. There's a lot more to spectrum theory now in forensic science, a lot more than what we did. You're going to learn about that next year if you take forensic science. It's a really interesting topic. But the concept of this is the fundamental part of it. But there's been a lot more development. They don't even use light spectrometry anymore. They use mass spectrometry. So it's a little bit different. Okay, but the concept is the same, that you can identify what something is made up of based on its spectral lines. How did this relate to our models of the atom? How did this relate to the models of the atom?
Doesn't one have to do with like Rutherford's, like how he did the experiment and it kind of correlates the atomic spectrum?
One of them does. Yeah, it's not Rutherford though. No.
It's Bohr, because he demonstrated the hydrogen one.
Yeah. What did Bohr try to say?
Um,
What did the electrons do?
when they get energy, they go to a higher level, and if they lose energy, they become more stable and get into good enough.
That's exactly right. So here's your nucleus. Here's your electron orbiting shell 1, orbiting shell 2, orbiting shell 3. Here is your electron. Now, the electron is much further from the nucleus than we see in this diagram, but I'm not obviously drawing it to scale. The electron gets hit by a photon of energy. It jumps up, let's say to orbit level 3. By absorbing that energy, it's able to jump up. But it wants to be grounded. So it wants to give that energy back off, believe it or not. So it's going to do that in the form of some light. Now, what Bohr noticed is that the difference in the energy levels is what gives you the spectral lines. So for example, if ground level is considered, let's say, 0 electron volts, level 1 is considered 1.5 electron volts, let's say level 2 is 5 electron volts. I'm giving you random numbers I'm picking. These are what's called the excitation states. Remember when we looked at that video real quick on fusion and fission, and the author of the video was using terms like electron volts. He was calling that the binding energy. That's kind of what's happening here. So if you go from level 0 to level 2, you need exactly 5 electron volts of energy. What if I get 4 electron volts of energy and I'm an electron, and 4 electron volts of energy hit me? What's going to happen here?
Nothing.
What's going to happen?
Nothing.
Why?
Because it can't go more than it does. Did you say that's 4? It doesn't have 5, so it can't reach that upper part.
Yeah, it can't. Where would it end up technically if you would? And what do we know?
They can't do that.
The whole concept that Bohr stated was that electrons are at specific discrete energy levels. So if I get 4 electron volts, I end up somewhere in between here. But according to Bohr, the concept was that you'd be at exact energy levels only. So an electron cannot absorb a fraction of the amount it needs. It needs an exact value. So let's say hypothetically we've got another electron over here. How much energy does it need to go up to the next level? 3.5. Because this level is 1.5, this level is 5. So to go to the next energy level up here, it would need to gain 3.5 electron volts. Okay, does the concept make sense that it needs to be discrete? You cannot have a fraction of a change in energy. It's got to be a discrete amount based on the actual energy levels.
So when it's being like combined with other electrons, it will just like, deny it if it's not the correct amount? Or is
If a photon hits an electron, it will not absorb the energy if it's not a specific amount. It has to be the exact amount of energy for it to absorb it and to gain that energy itself.
I don't really understand how it relates to atomic spectrum.
So you know how the atomic spectra produced all those lines on that black background?
Yeah.
The distances between those lines, those discrete distances, correlate to the energy levels here.
Okay.
Okay? I didn't go over, Marco, the exact correlation, but the idea is that the reason for those specific spectra that we see has to do with the energy levels for each element. Okay? Now, what's interesting is to see that we can relate this using Planck's constant. Okay, using E equals h omega. This is the second mathematical portion of the test. E stands for energy. That energy needs to be measured in joules. So I have to give you a conversion factor for this, and I will give it to you in the problem. So if we know, let's use this example here. Let's look at the second example here. We said that we needed 3.5 electron volts for this second level electron to jump to the third level. 3.5 electron volts were needed. So that would go in for E. The problem clearly though is that we have to multiply by some conversion factor to put it into joules. Then on the right hand side, Planck's constant is given. 663 times 10 to the negative 34. The units are, what are the units for Planck's constant? Would be joules seconds?
Yeah.
Joule seconds? Yeah. Joules times seconds there. Now, you would be given the conversion factor. Anybody remember the conversion factor though? It's actually an easy one to remember. It's not a random number. It's a specific number. Anybody remembers from class? It's the same number as the fundamental charge. 1.6 times 10 to the negative 19. Okay, it's the exact same number. It's no different. Okay, 1.6 times 10 to the negative 19 joules is the equivalent of 1 electron volt. So I put a 1 in the denominator, and I can clearly see EVs cancel. So I'd be multiplying this quantity times this quantity. Now, if you're doing the test and you forget to do that, your answer is not going to make any sense at all. You're going to get a number like this divided by a number like this. Well, I mean, I guess it would make sense, but the frequency level will be way off. You get a frequency on the order of 10 to the positive 35. Okay, so when you get an answer, think about the spectrum of the EM spectrum and what we looked at in class, and you could revisit your notes if you want to help yourself remember this. We looked at, the EM spectrum ranging up to gamma rays all the way from radio waves. So look at those frequencies. You're never going to get a frequency on that range of 10 to the 35, which is what we would get if we forgot to convert this right here. And if you divide by 6.63 times 10 to the negative 34, divide that into 3.5, you're going to get something times 10 to the positive 35, which is not reasonable as an answer. So we would get an answer here. I don't even know what we'd get. Let's divide through. We get an answer, and I don't even care what the answer is. What I care about is the significance of the answer. What are the units of omega?
Yep. Hertz.
Because it's a... What's omega stand for? Frequency. Okay, so it's something in hertz. So most likely I'll give you a question like this, and maybe I'll say what kind of electromagnetic radiation is produced by this process of spontaneous emission. And I have to give you a table. You have to look in the table and see where this fell in. Okay, what did we get for a number in the end? What did we get, Marco?
I got 8.45 times 10 to the 14.
Let's take a look, make sense of it. You're going to have negative 34 in the denominator, which makes that a positive 34. 34 minus 19 is going to be around 14. 30 over 6, or 35 over 6 is going to be... I don't know if I got 8 point... Anybody else get the same answer?
8.45.
8.45? Okay. The exponent portion is exactly right, so that looks good there. So, what you have to do is take a look at a table of values and consider where this lies in that table. So if you want to see what kind of a table I'm going to give you, look back at your notes when we looked at the EM spectrum. I gave you a table in there that shows you radio waves, infrared waves, visible spectrum, ultraviolet,
Is that this?
gamma.
What are you talking about?
No, it was like earlier in the year. Find it in your notes. It's like chapter 12 or 13, something way back, okay? But if you want to get an idea, you can practice. It'll be that table. Again, guys, everything in this class is cumulative. So if you struggle with that, make sure you revisit. I'm not going to revisit that now. So be familiar with that table, but I would give you the table, but knowing how to use it.
And that table's in chapter 12.
I don't remember, to be honest. Okay? Look back in your old stuff.
That's it.
Thank you.
What is it?
14.1.
14.1. Cool.
All right, let's talk about some of our stable and unstable. What keeps the nucleus stable? What a nucleus stable?
Strong force.
Strong force. The strong force only acts on small distances, which is why it works in the nucleus. The strong force is independent of charge. Therefore, neutrons and protons both feel an attractive strong force. Amongst each other, within each other, okay? So proton to proton, neutron to neutron, and proton to neutron. They feel an attractive force when it's at a small distance. What happens when the particle gets much, much bigger?
Is this 23 too?
25-1, 25-3.
Becomes more unstable
Yeah, it becomes more unstable. Do you remember why, Julia?
because the protons repel each other. To like get away, but the more neutrons you have, the more stable it is.
Okay, so what we're looking at here is a bigger and bigger and bigger nucleus. So the protons at the very end, they still repel each other with the electric force, with the Coulomb force, the electric force, but they don't have that attractive force anymore of the nuclear force because they're so far apart for a bigger particle. So what Julia mentioned at the end was, in order to make a bigger particle stable, we want more neutrons in the nucleus itself so that the nuclear force goes up, like the strong force goes up, but the electric force doesn't go up because neutrons don't have any repulsion, whereas protons do. How does this relate to nuclear fission? How does this topic relate to nuclear fission? Fission. Come on, relate what we're talking about, fission. Most of you answered this right in the quiz, so you should be able to answer this.
Well, fission is the combination of two nuclei, the fusion of two nuclei. The separation of two nuclei.
Of one nucleus.
Of one. Oh.
You're mixing up fusion and fission, yeah. Remember, fusion is two things coming together.
But
Fission.
separate. But wouldn't you have to have two nuclei together to refer to separate, or it's just one?
No,
kind of
it's,
cut in half?
so it's, imagine a nucleus that splits because it's unstable.
Okay.
So you have a nucleus, we did the example of uranium in class. It's the most common one that you'll see. So you have uranium nucleus, okay, and it has an abundance, and it's not stable, right? It's not stable at all. And it splits up into, I think it was barium and lithium in class. It doesn't matter right now what it was. So it splits up into two different things. Those two particles then split up further, or those cause a neutron to go off to affect the other uranium nuclei, which cause those to split. And as a result, fission produces energy because of the breaking of the bonds there. So you get energy as a result of fission because it breaks the particle up. Nuclear fission is usually used to produce energy, and it's usually used in a chain reaction form. Okay, nuclear fission. And again, that's for unstable elements. Unstable. Remember that we want stables to be we want elements to be unstable to produce nuclear fission. That's the whole idea. So nuclear fission is really controlled chain reactions. It's a chain reaction that you can monitor and regulate, as opposed to an uncontrolled chain reaction, which is really just a bomb. That's what a bomb is. Remember, a fission bomb is an uncontrolled nuclear reaction. We talked about the fact that we only use fission in nuclear reactors. We don't use fusion yet. We have not really been able to harness the power of fusion. It is more unstable in this case than fission is. So we haven't really gotten into fusion reactors. That was one of the things we talked about. Although the fusion reaction itself would generate more energy than a fission reaction ever would. Okay? Please study the rest of this tonight, folks.